Now we consider another interesting case. We consider the three-dimensional case. A surface S in R3 can also be described by parametrization. Can be parametrized by x is xuv, y is yuv, and z is zuv. Okay, you have studied analytic geometry. I think you know this. A curve can be parametrized by x equal xt, y equal yt, z equal to zt. For surface, you need two parameters, u and v. Okay, so these three equations can be grouped together to give a map. That is a map. This map, if the function x, y, z is continuously differentiable, then this is a C1 map. Phi from U to R3. Phi uv is x uv, y uv, z uv. Okay, so that our S is the image of this phi. Here the U is an open subset in R2. Now we take a P to be phi AB, a point in S where the point AB is belongs to U. Okay, we maybe we'll draw a picture here. So this is x, y, z. Our surface is here, and our phi is here. U, v. This is our set U. Okay. Okay. So this is the point AB. The image of this point is a point in the surface. That is our P. Okay. Now we want to find the normal vector of the surface S at the point P. We want to find the normal vector at P. How to find this normal vector N? This is the problem. To solve this problem, we consider this gamma, a curve gamma, U to gamma U is phi UB. Okay, that is we restrict our point in the in U parallel to the U axis. We consider the U here. So the UB, such a point is UB. So this line is mapped into the surface by a curve. When the point moves from the left to the right, parallel to the U axis in the parametrization domain U, then our point corresponding gamma U, which is phi UB, move on the surface from here, passing P, and then here. So this curve gamma, the tangent vector of this curve is gamma dot 0. So gamma dot 0 tangent. The tangent of this is gamma dot 0, which is the partial gamma dot A, not 0. Is the partial derivative of phi with respect to U at the point AB. That is the tangent vector of this curve. Okay. Of course, previously the tangent vector of the curve is gamma dot 0, but now we use gamma dot a, the derivative of gamma at a, because our p is now not gamma 0 but gamma a, is phi ab. Therefore, we need to take a derivative at a. The reason is similar to the case gamma dot 0. Okay. Anyway, we have a we have a curve on the surface. By fixing the second variable of phi, let the first variable change. We obtain a curve on the surface passing through the point P, and the derivative, the tangent of this curve at the point P is the partial derivative of phi with respect to u at the point AB, corresponding to the point P, corresponding to P. Similarly, we also have another curve, that is the tangent of this curve v phi av is the partial derivative of phi with respect to v, also at the point AB. So we have another curve passing through P on the surface, another curve here, and the tangent vector of that curve is gamma dot another, not gamma. We need to use another symbol to denote this curve, but I don't want to do this. By similarly, we know that the tangent is the partial derivative of phi with respect to v at the point. So we have two tangent vectors to two transversal curves on the surface passing through P. Our normal vector n should be perpendicular to both of these. Therefore, we can take n to be the cross product of these two tangent vector of the curves on the surface. We take their cross product or vector product. So that is n equals du phi ab cross dv phi ab. This is a normal vector of our surface S at the point P equal phi ab. Okay, so this is our conclusion. So how to compute this n? We give a more explicit component-wise expression for this n. N is the du phi cross dv phi. The partial derivative are evaluated at u equal to a and v equal to b. So I omitted it. So phi uv is x uv y uv z uv. Therefore, the partial derivative of u phi with respect to u is the partial derivative of x, y, and z with respect to u. Similarly, the partial derivative of the vector valued function phi with respect to v is x, v, y, v, and z, v. So their cross product, we know that the cross product is the determinant of I, j, k. I, j, k are the unit vector on the x, y, z axis of the three-dimensional coordinate system. So this is x, u, y, u, z, u, x, v, y, v, z, v. So the result is that y, u, z, u, y, v, z, v, z, u, x, u, z, v, x, v. The bar here, the pair of bar here means determinant. And maybe I will use our determinant notation. So that is determined. We expand this formally expand this determinant which respect to its first row. So we get determinant of YU for the first component ZU YV ZV, then determinant of ZU for the J, the coefficient of J is ZU XU ZV XV. Then finally the coefficient of K is XU YU XV YV. And using our notation for Jacobian determinant, that is the Jacobian of YZ which is respect to UV, and ZX which is respect to UV, and also XY which is respect to UV. So this is the cross product or vector product of these two tangent vectors of curves on the surface passing through the point P. So if this is capital N, the cross product is not zero. If this is not zero, then N is normal vector at the point P of S. Okay? But if this is zero, we have nothing to say. A zero vector could not be considered as normal vector. But once it is not zero, we can, this is the normal vector. Having obtained this normal vector, you can write the normal line and also the tangent plane, the equation of the normal line and the tangent plane. Okay. So this is a geometric application to study the tangent line, tangent vector, tangent line of a curve. Of course, once you can do this, you can write the equation of the normal plane of curves. And also we consider surface. We consider the surface given by fx equals 0, or the surface is given by x phi from U to Rn. R3. Okay. So the three-dimensional case, here we use the cross product to compute the normal vector n. So today we will stop here. We will study the n-dimensional case. I will let you know what we'll start next time. So a surface in Rn can be parameterized by a map phi from an n-dimensional, n-1 dimensional open subset to Rn. So if you want to draw a picture of this, you will also the picture is very similar to the three-dimensional case, because in the two-dimensional paper we could not draw higher dimensional pictures. So, but our reasoning is okay for higher dimension. Okay, so our surface is as a three-dimensional case is the image of the parametrization phi. Okay, so how to compute the normal of S at a point P is phi A for A in U. So this is our point P, and this is our S, and our S is the image of phi. Phi is n-1 dimensional. This is x1, u1. This is u1. This is un-1. So This is our U. The point P corresponding to the point A here. How to compute the normal vector of S at this point P. How to compute this? We will solve this problem next time.